Okay, let's look at find the centroid of the region bounded by y equals x squared and x equals y squared. So we're basically looking at a parabola that opens up and a parabola that opens sideways. So I guess the region of interest is right there, and we would need to find intersection points to figure out how to set up the limits of integration. So we can go look at this on our TI, and we can also do it algebraically. Just keep in mind that in your TI you can only put y as a function of x. So we would have to put this guy as y equals plus or minus square root of x if we want to see the top half and the bottom half. And it looks like we don't care about the bottom half, so we could just put in the top half of it into our TI. So I've got y equals x squared and y equals the positive square root of x just for the top half of the sideways parabola. Let me do a zoom standard, zoom 6. And as we had suspected, it's right there. Let's go zoom in at the origin. And there we are, and it looks like definitely 0, 0 is an intersection point, which we had seen anyway. And the other intersection point looks like it's 1, 1, and logically it makes sense that it would be 1, 1, but let's do a quick second trace, number 5 for intersect. Let me go closer to that intersection point, push enter once, twice, 3 times, and yep, that intersection point is 1, 1. Or if you wanted to do this algebraically, you could just use a substitution and say x is equal to y squared. Let me plug it in here. So y equals x was y squared squared. So that's going to give us y equals y to the 4th. And getting all the y's on one side will give us y cubed minus 1 equals 0. So y is 0 and y cubed minus 1 is 0 will give us y cubed is 1, which means y is 1. So our two intersection point, if y is 0 and I put it in here, let's say, I also get x equals 0. And if y is 1 and I put it in there, square the 1 and you get x equals 1. So as we saw with the TI, 0, 0 is x and y intersection point, and 1, 1 is the other intersection point. So first things first, we figured out how it's bounded between what two values are we looking at our integral. We're going to find the area next, and in finding the area I could do clearly a top minus bottom, top function minus bottom function, or I could also even do a right minus left and do a dy problem, but it's easy just to go ahead and do the dx problem as we see it here. So the top function is the sideways parabola, which got picked up from the positive square root of x here, minus, so again this piece was y is equal to square root of x, minus the bottom function is this parabola that's opening up, which is x squared dx. So top minus bottom, and I'm going through it from left to right from 0 to 1 are my limits of integration. So we end up with, this is x to the half, integrated x to the 3 halves over 3 halves, which is 2/3, minus x cubed over 3 from 0 to 1, and that's going to end up giving us a 1/3 if we punch it in. So we found the area of the region. Next I'm going to find x bar, so 1 over 1/3. For the area, a to b, I'm strictly keeping it at top minus bottom, so from 0 to 1. X times the top function, again, was the square root function, and the bottom function was the parabola, dx. So we end up with 1 over 1/3, 3, 0 to 1. Let's distribute this guy in. X to the half and x to the 1 is x to the 3 halves minus x cubed dx, and that's going to give me x to the 5 halves 2/5 and x to the 4th over 4 with a 3 outside from 0 to 1. And once we plug those values in, we're going to end up with 9 over 20 for our x bar. I want to point out that if you're using your TI, since this involves some fractional exponents and your TI uses approximation methods, your answer might be very close to 9 over 20, but not exactly. So it may give you sort of an irrational number that doesn't turn back into a fraction using the feature on your TI. So if it says exact answer, then you're going to have to go through the business and plug it in like I did and get the 9 over 20. But if it says approximate, you can just punch this into your TI and get an answer out. Okay, so now for our y bar, we have 1 over 1/3. Again, from 0 to 1 was our limits of integration, a half times the first function, the top function, which was the square root of x function, squared. Remember, top function was square root of x, bottom function was the x squared function, minus the x squared function, squared also dx. So we end up with square that, get an x, square that, x to the fourth, a nice polynomial function, and we're going to integrate that. And once we plug in 0 and 1, we actually get 9 over 20 for this as well. So our center of mass is 9 over 20, 9 over 20. So approximately, actually 9 over 20, we don't even have to approximate. It's going to be 0.45, comma 0.45. Now let's go look at the graph and see if this makes sense. And to get an accurate graph, we said we're going to look at our TI. So here I am at the TI, and let me do a zoom square so that things don't look distorted. And if I go to the window and zoom in a little bit more, let's go -2 to 2. -2 to 2. And again, my zoom was it. Actually, I wanted it to be square. So I wanted to get a good idea. Okay, so this region, let's see if this makes sense why the x and the y coordinate ended up being exactly the same. If we look at this region, there's actually symmetry involved. I went in and zoomed in a little bit more. Now, why does it make sense that the x-coordinate and the y-coordinate of the centroid were the same? Well, notice there's symmetry going on here. There's a line of symmetry about the line y equals x. And we had said that if there's symmetry involved when we were doing the derivations, that your centroid would have to lie on the line of symmetry. And this is clearly symmetric about the line y equals x. And so therefore, my centroid must lie on that line y equals x. And if it lies on the line y equals x, the x and the y coordinate have to be equal because y equal x is the line of symmetry for it. And it looks like it's 0.45, and that also makes sense because this kind of seems bottom heavy rather than like bottom left heavy rather than the top right heavy. So instead of right smack in the middle at a half, it's a little bit more towards 0.45, 0.45. So things are making perfect sense by looking at the graph. Due to symmetry, the x and the y coordinate have to be the same here. Let's go look at one more example. Okay, we are to approximate the centroid of the region bounded by the sine curve, the cosine curve over that interval between 0 and 4. So we know the sine curve is going to look like that, periodic, and we know that the cosine curve is going to look like, let me be a little bit more clear. Let me do it a little bit more clearly. We will go look at the TI, but just to recall, the sine curve again is going to have its max at pi over 2 and min at 3 pi over 2 at -1. And then we have our cosine curve that looks something like, let's do that in another color. It looks to have its minimum at pi getting a -1 and its maximums at 0 and 2 pi going to 1. And they want us to look at the sine and the cosine curve between 0 and pi over 2 and at pi over 4, and at pi over 4 we do know that the sine and the cosine curve have the same value of 1 over root 2. So it looks like if I were to do this by hand, this is the guy I'm interested in, if I were to look at it by hand, but we'll go look at it with our TI also. So I got sine x, cosine x, and for my window I'm going to go from 0 to pi over 4, because that's the x values that they gave me. And I'm going to maybe go from Sure, -1 to 1 seems fine because we know that's where the max and the min are. So there is our sine function, and there is our cosine function, and they meet at that pi/4 as we had suspected. So that's the region, or this is the region that we're interested in finding the centroid for. Now let's go do the math. So let's find the area first, again because the intersection point is at pi/4, and you can check that because sine of pi/4 and cosine of pi/4 are both 1/√2, that's where they intersect. And top minus bottom function, my top one, I actually have that backwards. My top one here is the cosine curve. Let me fix that. My top, the red curve, is the cosine curve, and the bottom function is the sine curve. These are easy to integrate. So this guy goes to sine x, that goes to minus cosine x, so we get a plus there. We punch those in, and we end up with 1/√2 plus another 1/√2, and we take cosine of pi/2 minus, it looks like sine of 0 is 0 and cosine of 0 is 1. So 2/√2 minus 1 is what we get for the area. I went ahead and rationalized this. I don't have to, but I just wanted a little bit cleaner, so I end up with √2 minus 1 for the area. Okay, let's find x bar. That's going to be 1 over the area from 0 to pi/4, x times the top function, which was the cosine function, and the bottom function, which is the sine function, dx. Now, since the direction said approximate, I feel okay to go ahead and use my TI on this guy. If it didn't say approximate, I would have to do a by parts problem. Remember, x cosine x minus x sine x, you could split that up into two integrals. Let u be x, your dv be cosine x, and then do uv minus v du. So if it said find exactly, I would have to go do a by parts, but if it's saying approximate, I'm going to use my TI. So let's go put this guy in. Math 9, I have x times that quantity. Cosine of x, close your parentheses, minus sine of x, close your parentheses and close them again because you had opened it here to multiply the x through, comma x, comma from 0, comma to pi/4. So there's what we get for that piece. That multiplied by what's outside, times 1 divided by the quantity rat2, close it, minus 1, and then close your parentheses because you were dividing by an expression in the denominator. And it looks like we get approximately 0.27 for the x bar value. Now let's go find y bar. So 1 over the area times the integral of 0 to pi/4, a half, square your top function, which was the cosine function, that's cosine squared, and the bottom function, which is sine squared. And again, I'm going to use the TI, although this integral would be much easier to use TI calculator than this guy, because this is a by parts x cos x and x sine x. But this, with an identity, you could technically change that to cosine of 2x, which would be much quicker to integrate. But we're going to use our TI. So I did math 9, parentheses cosine x, close parentheses, and square the whole thing, minus sine x, all the whole thing enclosed in parentheses squared, from 0 to pi/4. So this piece is just a half. I'm going to now multiply by this other half that I didn't put in there. And then I'll multiply it by this guy. So that answer multiplied by a half and by the other guy, and we get approximately 0.60 for the y coordinate of the centroid. Now I'm back on my graph, just trying to get an idea of whether this makes sense or not. So around 0.27 for the x coordinate. I used trace to trace it there, and then 0.6-ish for the y coordinate, so higher, closer to 1 up there, which kind of makes sense because it's sort of top heavy. So right around there is where our center of mass would be for this problem. So at this point, if you wanted to do those integrals by hand for x bar and y bar, I've shown the work here. The first one is a by parts, the second one uses an identity. Pause the video and look at it and make sure it makes sense if you were to do it by hand.